So let's kind of talk a little bit about this, right? In today's rapidly growing network, we're adding devices, we're doing changes, so many things are happening. I mean, you can see how complex that design is. We do a lot of stuff. But our goal is to get to 5.9 goals, right? Enterprise class availability. How do we do that is what we're going to be talking about today. I really want to just kind of give you some hints, some tools, some design guidelines to get you going, talk about how we can do this from the physical layer, from the software layer, from the network itself, and see what I can do. Like I said, I cannot answer every possible design pattern that you guys have. It's impossible to cover that many number of people. But hopefully I'll give you enough stuff that you can take away and you're walking away, you're understanding a little bit more why we do the things we can, why we can do some things, and how we do things better and how we can improve on that design. So, like I said, I'm going to cover a couple of things. I'm going to first talk about an intro, just a brief idea, because it's a 2-level class. It's not an advanced class. If you guys are advanced, then I apologize. I'm trying to cover as much as I can from the respect of everybody who's here. We will talk about system-level availability, how redundant components help you keep the network or the devices alive in the network so they don't go down. And then we'll talk about software things like process restart, ISSU capabilities, GIR, other things that will help you keep the network or switch your versions because that's some things you want to be able to do. And then finally, we'll go into the network level availability and how we can do things on the network, how the network has evolved from what it was today to the future, and what things you can do there to make it better. Okay? The agenda makes sense? Are we on the same page, guys? Can you hear me well in the back? Very good, I'm glad. Okay, so we're going to be covering 2 kind of things. We're going to be talking about some unplanned outages that will happen in your network that are out of your control. Things will happen, software will evolve, you have a problem, there is a bug, there's a PCERT, all kinds of things can happen. So how do we cover that? What kind of things we want to cover? And then we'll talk about planned kind of things like when I'm changing my software version, what can I do about it? How do I take care of ISSU in the Nexus devices? Talk about process restart capabilities, patching, all kinds of things there. And then also GIR for hardware replacement or hardware maintenance that we'll be talking about. Now that we've covered that, let me give you a brief introduction about myself. My name is Samer Tidosi. I've been with Cisco for almost 3 decades. So I've been all over the map in Cisco. I've actually covered every single product line, maybe except for the LS1010. That's the only one I didn't work on. I'm in infrastructure. I am an engineer. I am not a TME. I'm not a product marketing. So I'm actually an engineer. I work on the stuff that I'm talking about. And I love to be here talking to customers to get your feedback, to understand the problems so we can actually take this and do the design. As I said, I'm a distinguished engineer. I've been with them since dinosaurs existed and probably will be there for the rest of my career. That's the hope. And then I have a family, a wife and 2 kids and a small dog. We love to do a lot of stuff outside. As a kind of a side thing, during my career at Cisco, I actually worked or led a band. I was a singer in a band and I published 2 CDs. It was a fun thing. Then they got me working on high availability, and I had no time, so I had to quit. No, I'm just kidding. 2017, I actually switched focus. I actually started working as a coach and playing basketball with my kids, something I love to do, and I got a chance to play with them on the same court, as you can see in the picture. So this is an advantage. I actually beat LeBron. I did it before he played with his son, so that's kind of a fun thing for me. And I'm a technology enthusiast. I love to do a lot of stuff, a lot of do automation, so all kinds of things. One prominent thing to mention is I was probably one of the original designers of ISSU on the 4K, if you guys are familiar with the Catalyst 4K, if you used it before, which has evolved into the 9400 right now. So we designed that one. We won a Pioneer Award. It was first of class in 2006. And we've actually taken that and tried to move it to a bunch of places. There are 2 main competing things that kind of gets us to measure availability. One is the mean time between failures, and one is the mean time to repair a network. Now, mean time between failures, I really have no control over. This comes from devices. As you guys are aware, right? New ASICs come out, new components come out. They have a certain MTBF that is associated with it. It's going to be 10 years, it's going to be 20 years before failures. I can't control that. But if we can, that'll be awesome. That will increase availability. The one I have control over is the mean time to repair a network. So if I can fix the problem fast, we can also get better availability. And that's really what we're going to be focusing on, is how do I fix the network fast? And this is where redundancy comes into the picture, right? So we really want to get to the 5 goals. The equation is very simple. Availability equals the mean time between failures divided by that one plus the mean time to repair. So as the mean time between repair gets smaller, you can see that the number gets closer to 1. And that's really what we're trying to get to. So if we take a device that is about 10,000 hours of failure, so I can see, I don't know if you can see my pointer, 87,600 hours happens to be 10,000 years, 10 years, right? So if it's a 10-year failure between failures that they're rated, and we were able to fix the device or a problem that happens on this device within 24 hours, I get into 3 9 domains. Still a reasonable number, about 2 hours of downtime a year. Not too bad, but that's not where we're going to go. We're trying to get to 5 nines. So if I can make it 4 hours, I'm a little closer. I'm like 4 8s, 4 9s and an 8, much, much closer. You move on to sub-second convergence, and I can do it within less than a minute. Now I'm into my 5 9s, and I'm getting much, much closer to my goal. Cool? So, like I said, I cannot control the MTBF. As devices evolve, their MTBF will increase, but we can really work on the mean time to repair network, and that's our goal to get to the 5 nines. Now, there is one other thing that comes into play, right? Regardless if the rating of the device is considered to be 5 nines or even 6 nines or 7 nines. If I don't have redundancy in my network, and you have thousands of devices, as you multiply those across each other and the serial effect, the magnitude of the number changes. So if you look at the left side, I have 2 devices that are connected in serial. They're rated at 5 nines. Awesome. But the predicted availability of my network is less than 5 nines. It's actually 3 nines and an 8, because the multiplication of the 2 serial effects makes it a lot smaller. So this is where redundancy comes in the picture. So if I have a redundant component, even though the same devices are rated at 5 nines, I'm getting into 7 or 8 9 domains, and that's really what we want to get to. So I want to increase my availability as much as I can, so that if a serial effect does come into play, it doesn't drop me back, and I want to be there within that domain. Makes a lot of sense? Are we all on the same page? Very good. You guys know all of this? Okay. Like I said, this is a middle-level class. It's not an advanced class. It's not a basic class, so we're trying to cover both aspects, and we'll go from there. Like I said, I'm going to be talking about 3 things. I'm going to talk about network level availability. What can I do in the network? If I cross-mesh everything and connect everything together, then awesome. I can do that. I can have all the paths in the world, then I'll have no failures. What can I do from the device level itself? Do I have redundant power supplies, redundant fans, so that the device doesn't overheat or it doesn't lose power, and I can continue to work in the network? And then from the software side, we'll talk about what Nexus offers that allows you to be highly available. How can you change your software and the things like that? Very good. Are we okay so far, guys, for that? So this is the basic intro. Like I said, sorry for the advanced people. We'll discover it and we'll move on. Now we're going to be talking about how do we do things from the data center itself. So from the data center availability, we have many things that we can do. Right? On the unplanned events itself, I've talked, we're going to be covering things. We do support SSO, which is stateful switchover between redundant components. We do support graceful restart. We do support process restart. We have the capability for non-stop forwarding as well. So we're going to be covering kind of a little bit of that and what we do from the software side. From the controller side, we have rolling controller upgrades we can do. Then we have the software itself. I've talked about, we're going to be talking about ISSU, software maintenance patch, which is SMO, or what you guys refer as a patch in the field if you have a bug in some specific software. And then from the device replacements, from the controller itself as well as from the devices itself, what we can do. And we have a concept of a GIR that I'll introduce. If you're familiar with it, awesome. If not, I'll be introducing it today from the Nexus, so you guys can use that to replace hardware in your network as well. So planning is a big, big thing that you really, really need to look at. What can you do? How much money are you willing to spend on your high availability network? Do you want to replace, you want to make everything redundant? Awesome. If you have the cash for it, go for it. That will make it awesome. Do you really need to do? Not really. Where is important to you? What aspects of the network is important? So you have to kind of plan that and figure out what is the relevant things that you're going to be covering. Do you really need to use modular devices in the core? Can we do something else? I'll talk about that when we get to network level. What is the new evolution of the network? What are we doing? We're using form-fixed factors to do that, and that's actually much cheaper, so you don't have to spend the money. So we'll kind of be covering that. So this is, keep in mind, maintaining your network in a modular fashion, modular chassis, kind of like that. So the data center network has evolved from the basic core. This is what we used to call before access, distribution, and core. We've moved away from that, and we actually, because of the EVPN introduction and VXLAN, we use a whole lot of stuff related to leaf, spine, fabrics, and super spines. So we'll be talking about that when we get to the network level. And that's actually the evolution of the data center, how we've been doing it. It allows us to do a lot of things in a modular fashion. So I can build a block. I can actually replicate that block to get a scale out. I can actually use this in a modular, in a hierarchical fashion, so I can define what each of the layer will do. My learning will be faster, my switchovers will be faster, my conversions in the network will be faster. So all kind of things come into this picture with this new architecture. When we get to the network level, this is the picture you're going to be seeing. I'll be talking about it in a lot more detail. I just wanted to introduce it here so you're aware that we're moving away from the basic concept into this kind of style. Any questions so far, guys? The question is the PDF file in the session, yes. If you are registered on the session, it should be there. If it's not pushed, let me know. Send me a message in the WebEx, and I will push it again. Okay. But you should have it there as well. Okay. Question. QR code, so you can take a picture and join the Yeah. Okay. I'll go back to it quickly. I don't think it's here. Actually, you probably have to do it from your thing. The QR. This is a generic slide, so it won't actually have the QR code. Remind me after, I'll give it to you. You can actually join it, okay? Okay. So no questions so far? Is that because it's too early in the morning, or did I lose you guys? Which one is it? Or it's very clear. Maybe it's the third one. I don't know. Hopefully it's the third one. But okay. All right, let's talk about physical redundancy. So we'll start at the lower layer, at the switch itself. What can we do from physical redundancy to give me better availability in my design, and how can I keep the system alive so it doesn't even go down in the first place? We have two types of devices on the Nexus that we offer. There's the Tor devices that kind of fall into the 93, 9400 series. And there is the modular devices, which is the 9500 and the new 9800 that got introduced recently, right? The 94 and the 9300 come in a 1, 2, or a 4 RU factors. They don't have supervisor redundancy. They really only have redundancy on the fan and the power supply layer. So there is no supervisor redundancy, so I can't offer SSO in that one. So we'll talk about how we do the ISSU story and how we can actually upgrade the software without causing a problem, what things you can do to improve there. From the modular side, we don't do ISSU. Why don't we do ISSU? I don't know. Something that was done before I joined the data center team, but it's been like that. So only on the 7Ks, which is predecessor to this modular, we do offer ISSU. We don't have ISSU capabilities on the modular devices, but they do offer redundant supervisors, so we do have SSO capabilities, so I can do switchovers there if I need to, on top of the fan and the power supply redundancy. Okay, so keep that in mind as we talk, and that's where there's a bunch of other concepts that will help you replace your software or upgrade your software without causing any glitches there too as well. If I look at just the chassis from the front, this is what it looks like. I have a bunch of line cards depending on whether I'm on 1 RU, 2 RU, modular device, etc. You have the redundant supervisors if it is a modular. You won't have that if it's a top of rack devices. And you have the power supplies and the redundant power supplies that you can use. Now, like I said, on redundant supervisors, we have, and I'm taking an example of a 9500, 9800 sits similar. There's either a 4-slot chassis, 8-slot chassis, 16-slot chassis. The capabilities are different. You have 400 gigs now, even 800 gigs got introduced, so you can do a whole lot of bandwidth. And we do support redundant supervisors, so you have SSO capability that I can send between the active and the standby. So if a failure occurs on my supervisor, I can switch over, continue to work in the network, no impact. If I look at the output of the show redundancy, you can see there is basically, oops, where did it go? So you can see that you have an active supervisor and a standby supervisor, and it kind of says HA standby. I don't know if you can read that in the back. If not, you can look at it in the PDF. It kind of says that this has been synchronized, so I'm ready to take over if a failure does occur. This is how you check your status to see if SSO has been completed. Now, on the power supply, we have multiple modes where we can deploy. A question?
So are you recommending dual supervisors and redundant chassis?
So the question is, do I recommend having dual supervisors in modular chassis? The answer is yes, for many reasons. One is Cisco gets a lot more money. No, I'm just kidding. That's not the reason. That's not the reason I recommend it. But no, you need it because if you do have a failure on your active supervisor, your whole device is going to go down. So if you do have a second standby and it actually synchronizes the state, if a failure does occur on your active supervisor, which it might happen for software problems or something else, then you actually switch over and you continue to provide, and the network does not see any glitch from that device point of view. So it's recommended that you do it. Again, like I said, your planning will determine what you're going to do. Are you planning that? Is that in your core? Are you in VPC mode? Are you actually have redundant path to everything that if this fails, you have another path? You may not need it. So like I said, I recommend that you do it. But again, it's how the network is designed, how you deploy it, where it is deployed, and how it is being used. So that will determine it. But absolutely, I mean, if you can do it and afford it, absolutely it's better. Okay? Did I answer your question? Okay, great. Any other questions before I go to power supply redundancy? Okay, good. So talk about power supplies. We have 3 modes that we can deploy the power supplies in on the Nexus devices. Whether it's a Tor, whether it's a modular, it doesn't really matter. The first one is a simple one. It's basically a non-redundant whatsoever. It's just a combined mode. So that means all power supplies that are in the rack provide to all the line cards and everything that you have available in the system. They're not redundant, so if one of them goes down and you're actually oversubscribed, you may have a problem. But if you're not oversubscribed, then the other ones may cover you. Now, there's another mode called the PS redundant mode, where we basically keep one of the power supplies as a standby power supply. We don't actually have it participate in the combined mode. So the total output is only, in this case, if you have 4 of them, the 3 are actually combined, providing the output of the network. And the 4th one is sitting idle. So if one of them fails, you will actually kick that in. It becomes active, as you can see on the right side, and the failed one is actually declared dead. And then you get an alarm, of course, so you can go and replace it, switch it out, swap it with something else. Okay. So that's the 2 first modes that we have. Then there is an interesting mode for bigger chassis. It's called the in-grid mode. This is a unique mode where the line cards are kind of split into half. So the first half of the line cards is in a grid A, and the second part is in grid B. This is used in probably unique situations where you have a need to have more power supplies supplying something into special cards that you don't want to afford to go down, but you have to configure it in that way, and you have to make sure that your lines are connected. Are you using this one? I'm not really sure how many people are actually using this one. I just want to tell you guys about it so you're aware. If you need to use it, then this is a mode that we actually have, but this is mostly on the modular chassis. It's not really on the TORs. We don't have many line cards there. Make sense? Question? So the question is there any difference between option 2 and option 1?
Use case.
A use case. I mean,
I always use number 1.
if you have so the question is, do I have a use case for the special case number 2? I mean, not really. I don't have any use case. And just like I said, we have these capabilities. We let you do it. If you think you don't really need enough power supplies in your node, I mean, if you're oversubscribed and you need a whole lot of power, then option 1 is probably better for you. If you're not oversubscribed and you have the capability where you have one supervisor sitting there, not really used, or a power supply not used, then maybe you can go down this path. I don't see a difference between them as much. Like I said, most of the people actually live in the first domain. This is just an option we have. I don't know how many people are using it for that reason, but this is a good example to have for redundancy. Another question. The question is, can you run the power supplies in different voltages? I am not really sure if you can mix and match voltages. I haven't seen it. I know you can run bigger capacity power supplies that are different. So you can have like a 60 watt and then like a 120 watt capacity. But I'm not sure about if the voltage can vary. That I'm not really sure. I'll have to check. Let me confirm that, and I'll get back to you in the chat, okay? Any other questions, guys? One question. So the question is, in this mode, is the standby power supply that's the green here powered off? Yeah, it's not providing any power. Only the first three that are playing are actually providing power. This one is just sitting idle. So it's actually there. So like I said, I don't really know if there's a good use case for this one. Maybe if their power supply is burning out and you want to keep one spare ready to go, then that's a possibility, but I'm not sure. Okay, very good. Okay. All right, any questions on the grid mode? No? Unique, very unique mode, right? Okay. Okay, so if we look at the back panel, just quickly, there's fabric modules. These are mostly in the modular chassis. They provide support for redundancy as well as for distribution of the traffic. The fans, multiple fans are there to keep the system cool. The fans do actually play together, so if one of them shuts down, the other ones increase their speed so they can actually keep the system cool and you don't overheat. Now, if you reach down to a minimum number of fans, it may not be enough to cool the system, so you have to keep that. And you also get alarms when you have a problem like that. And finally, chassis controllers these are the ones for EOBC transmission and distribution of some traffic that are used, that are mostly in the modular chassis. The new designs of the 9800s doesn't have that anymore, so that's actually something going away from in the 9800 devices. Commands, just to show an output. If you look at a modular chassis, you have a bunch of fabric modules. You have a couple of supervisor modules that are in active and standby mode, and the same thing for system controllers, so we do provide redundancy across the level. Again, you don't have to have them that way, like he asked. Is it really needed? It depends where you're displaying this and where you're distributing these in your network, so you determine accordingly what your needs are. If you look at the command output, this is something that I just kind of configured in my lab. I have it in a PS redundant mode, but I only have one power supply. So it kind of shows that even though I'm configured in redundant mode, you can see that it shows that I'm not redundant because I have the second one shut down. So I have one chassis configured in that mode with one power supply, so it kind of tells me. So if you look at the power output, you can tell what mode you are in, if there's any problems, something like that, so you can actually display it, look at the alarms, and fix it, okay? But not necessarily a good use case, but it's just an example to just kind of reflect that. So far, so good on the redundancy? The question is there different parts for the fans that are running in the back as first in the front? So the question is there a difference between intake and exhaust side? I think we only have one fans that go in the back. I don't think we have any fans in the front. We do have different cooling stuff that goes for the ASICs that are on the motherboard itself, but not necessarily the fans. The fans are only plug-in from the back. I don't think. Very good question. The good question is about the fan flow. Is there like a specific parts? I am not a hardware kind of guy. I don't know. I haven't played with the fans exactly, so I don't know if they look different. I think there is, but I don't know the part numbers.
The power supply that is with the PE is the port side exhaust, and the ones with the PI is the port side intake. So I think the color of it actually, if I'm right, the PI is port side intake in red color. If you see the power supply and the fans actually, the knobs will be red, and the other one is.
There you go. So just so you guys hear it, I mean, he said there is two different parts. Thank you for answering that. There's two different parts, like he said, the red one, a PI and a PE for different parts. So I have to look at it because I haven't played with it. I usually just use the devices and just use them as is. I don't really hardly change the fans in the system. Any other questions before we go on the software side, guys? Are we good on time? Yeah, we're okay. All right. So let's talk about what we do on the software side. And before I do that, I want to just kind of give a brief introduction about the Nexus architecture so you're aware of it, right? The way the Nexus architecture evolved is very unique. It's distributed, very modular. But it has one difference that I haven't seen in any other systems in the world, including Cisco itself, right? Within the Nexus, we actually have a full control plane and data plane separation. That allows us to do a whole lot of things like process restart, ISSU, with zero traffic loss. That is something I haven't seen in any other devices. If it is evolved, then I didn't hear about it, but mostly I haven't seen anything like this. Even within Cisco, for sure, we don't have anything. This is the best of class. It evolved like that with a full data plane and control plane separation. We do offer the capability for service restartability, which I'll talk about in a minute. And then, like I said, because of the control plane, data plane separation, we can do ISSU, and I'll show you how we kind of do that today. We also actually made this even open source, model driven, so we have a whole lot of different things that we can add to it, like REST, GNMI, GNOI, all the new stuff is coming in open config, everything is available, telemetry capabilities, and the addition is the app hosting capabilities where we can basically host third-party applications that you can write from Nexus API, or like Thousand Eyes that we integrated in Cisco, Splunk, all other things that allows us to work together and then display the data and send it to other places in the network. So this is just one thing that is there. If you look at the ACI architecture, the ACI architecture is a little bit different. Even though we run the same exact software, we run the same exact hardware, the ecosystem for ACI is different. So if you're deploying ACI versus standalone, keep that in mind because APIC integration is key. We don't have ACI deployed without the controller. We can do standalone without it, and hence the name, standalone. You don't really need a controller. You can create your own. You can do NDFC, which is our controller, but you don't have to. You can actually deploy it on its own, run it from CLI. So this is where APIC becomes a big part of this network, where you can actually do the control of the policy, you can do control of the CLI. It pushes it out to all the devices. When we talk about ISSU, in terms of ACI, we actually call it an upgrade because we really don't have an in-service software upgrade where we are hitless. It's actually a little bit different because the way that the ACI integration is done with the APIC, we have the controller that handles everything. Most of the stuff is deployed in VPC pairs. So you basically can take one, swap it to the other one, and then switch back. So we don't actually have an ISSU story. Will we ever add one? I don't know. But right now, we don't have one. So we have an upgrade story for ACI. We don't have an ISSU story for ACI. Just standalone covers it because of the case that is standalone. So let's talk about process restart. Process restart. This is one of the capabilities we can offer on the Nexus that allows you to maintain the system running. So if you have a glitch in the software or you have a problem where one of the processes dies. So we have the capability of checkpointing our state to something called the persistent storage, which is the PSS. That allows us to maintain the running state, the configured state, all information about the process. If the process does happen to restart, then you basically will restart the process, it will fail, it'll come back, and it will restore its state from the persistent storage, and everything will be fine. So you don't even notice this happening. It usually happens well within 10 milliseconds of time. So it's really, really, really fast. You won't even notice it. How do you know that a process restarted? If you look at this CLI, you can actually display this for any of the processes that you have in the network as long as you know the name of the process. This example is BFD, for example. You can look at the number of restarts, and it will tell you that this process has restarted once. So if you see one, don't get alarmed. As the system boots up, every single process gets a number of 1, except for 1, which is Nexus API. It goes 2 times because we have to reload it twice. Everything else is actually once. It's just the way that the design of that process happened. But so if you see 1, that means your system is operating normally. There is no problems in your network. You have not had a restart. Is that deceiving? Maybe it is. It's just this is more of a command that we use to just check the state of the system. Now, there is multiple policies that you can enable for each of these devices or each of the processes within the devices. Okay, and then they separate a little bit when we get to the bottom layer. I put them in a different color. I don't know if you can tell the color difference. But the first 3 is the capability for stateful restart, which is basically a process will store its state. When it comes back, it will restore its state. That can happen both on a modular chassis as well as a single supervisor chassis. if you can do a stateless restart. Stateless restart means when I restart, I will replay my configuration back because there is some problem that I found that is not working. Maybe it's the configuration itself that's causing a problem. So I can bring the process back in a clean slate and then replay my configuration to reapply the state to its memory, which is possible. Or I can do no restart at all and keep the process down. Something like SNMP that may be not necessarily used in a whole lot of places. Some people may configure it to say, if it fails multiple times, I don't really care. It's not necessarily needed in my network, or any process for that matter that you care about, that you can do that. You can keep it in that state. If you go onto the concept of the modular chassis now, I can actually reset the process, or I can reset the box. So if it's a modular chassis, I'm allowed to do a switchover, because if I reset my active supervisor or the line cards, then I switch over to the new supervisor. But in the case of the EOR, I can't do that. I will end up reloading the soup. And then I can configure a switchover itself if I'm in a modular chassis. I can say choose. So you can basically cascade these policies. The cool thing about it is you can start at the top and make the policies go one by one. So you try this one 3 times. You don't like it, then you go to the next one, and so forth. These usually come pre-configured into the Nexus in the configuration files, but you can talk to your marketing team or the TME team. They can help adjust this if you really need it. You can configure them yourself on your devices. Okay, so this is a capability that allows you to do that. I don't necessarily recommend that you guys change this because we probably tweaked it a lot to make it work for what we need, but there are special cases that you may need to tweak these policies and configure them on your devices. Any question on process restart? Question?
Is there any reason or where you would have an advantage with a single soup over a dual soup?
The question is, what's the advantage between a single soup and a dual soup?
Or would there be? Where is there I guess a use case, if you want to use that word, where a single soup would, that's what I'd want to go with.
So the question is, where is a good advantage for using a single soup versus a dual soup, right? Okay, so all our Tor devices are single soup devices. And this is where we place them in the top of the rack. So we don't have dual supervisors in those devices anyway. So they're placed there for a fact. Now, in the core, like I said, in the core, I'm repeating to kind of some of the same question he alluded to before. You can use it as a single soup in a dual supervisor chassis, or you can deploy as a dual supervisor depending on how you configure them, if they're in VPC mode or not in VPC mode. So it's the advantage if you have a single core in your network or the second layer, the spine, where you don't have a second path, then you probably need a second supervisor. But if you have a second path, you probably don't. And then, like I said, when I get to the network, we'll talk about it because we're moving away from using modular devices. Actually, we're moving mostly to Tor devices. So you can see that it's not that much, but if you have dual supervisor devices, I recommend you deploy the second soup because it lets you get an advantage. Okay. Any other question? The question is, why do we have process restart happening? Yes. So I'll give you a very simple answer. I have 1,500 people who work on the Nexus software, and not everybody writes beautiful code. So we will have problems. It's very simple, right? I mean, the rule is for every 50 lines of code, I may have one bug. So if you happen to hit that one, the process may crash for whatever reason. Maybe we divide by 0, maybe I'm allocating out-of-band memory, I'm using more than I need. So software problems happen all the time. So we're trying to just make sure that the system recovers and it doesn't have a problem. You don't want to end up losing your system and then shutting it down. So a lot of people write software. We can't assume that everything is fantastic and I write 100% accurate software. Maybe with ChatGPT nowadays, I can maybe cheat a little bit, but not really. But we still have some bugs in the software. So it's very normal to hit it. Sometimes it's a configuration issue due to your network that you have some packets coming in that are corrupted and we don't handle it very well. So as simple as that. Okay. Any other questions so far? Okay. Let's talk about nonstop forwarding. So what is unique about Nexus for nonstop forwarding? Nonstop forwarding has been around for a while. Nexus came into the ecosystem after GR was introduced or the graceful restart concept was introduced in the IETF. So we were deployed with IETF standards from the get-go. We didn't have to actually do our own implementation. This came from Cisco way before the IETF implementation came. So devices like the Catalyst support 2 modes. They have the Cisco supported mode as well as the IETF mode. However, Nexus, since we came after this was introduced, we decided to go directly for the implementation of the IITF. We didn't actually do our own proprietary solution. Only one protocol we have. Does anybody know which one that one is? EIGRP. EIGRP is the only protocol in the world that has not been open standard. It's still a Cisco proprietary protocol. So that's the only one that does not support the standards. Other than that, everything else has moved to standards. Okay, so we don't have to do any additional configuration. By default, when you boot up your box, you're already capable for GR or for NSF forwarding. So you can just tweak the timers if you want. That's something you can play with if you want to make it a little longer, to say, okay, I may be taking a little bit longer to configure my system or come back in the network or reconverge, so you can change that. Other than that, you don't need to do anything. By default, it's already capable. Now, what does that mean? Like I said, the only other protocol is the EIGRP. Means that when I'm playing around or I'm talking to other devices in the network, as long as they're supporting the IITF implementation, Nexus devices can talk to them and they can restore state and get state from there, no problems. If you are talking about devices that are not capable, like Catalyst devices, and they're being configured in the Cisco proprietary, then I can't actually talk to that device. I will actually be able to talk to other devices. So I can only talk to the device on the left because it's configured in IITF mode. That one is configured in Cisco-specific mode. Then it will only talk to Cisco-specific devices to be able to restore its state. Will we ever move away from it? Probably. But at this point, we do support it because some people have older legacy devices on the Catalyst to do that. But for the Nexus devices, you don't have to worry about it. Now, how does GR or NSF work? Very simple. When I'm about to take down a protocol or do it, I will send an LSA into my devices and say, I'm about to go down. Just be aware, don't talk to me for a bit. I'll let you know when I'm coming back. The devices will basically get an act, say, okay, I got you, we got you covered. When you come back, we will send you all the data you need. The process will go through that restart at that point. Because of the separation, I continue to forward path along the well-known paths into my data plane. So there is no impact to your data plane. You don't see anything at all. The device will come back. The process will restart. It will restore its state, whatever it has in the PSS, and then it will send a message back, says, I am back in the network. Please feed me all your information. So all the BGP routes, all the other routes, OSPF, everything, I get that. And then I can install that with my hardware, and I'm ready to go. I'm back in the network. I'm reconverged. So some of it we can store locally, but sometimes the magnitude of data is huge. I can't store it locally within the device because of the memory. Then I will actually ask my peer network to give me the data, and this is where NSF comes in the picture. Okay. This is just for your information if you want to look at the RFCs. Like I said, EIGRP, you can see that Cisco proprietary. We don't actually support it. It's not an IITF protocol. So far, so good. Can we get into patching and ISSU? Fun stuff? Okay. Let's talk about patching. So in your network, sometimes you have a problem, like I said. The gentleman will ask, why did my process die? I have a problem. We found a bug. I'm not handling a divide by zero correctly, so I need to provide you a patch. So what do? We actually send you a small RPM signature, small. It has only that process or anything that is impacted. And then we send you a README file with it. Okay? The README file contains information about the metadata of, this is the bug ID we hit, here's the problem, this is what it has. And it has a reload type on the bottom. And the reload type basically tells you whether this is going to be a graceful patch or does it require you to take the device down and reboot it. Now, we have two supported types in Nexus. We have a non-reload or a hot patch smooth is what we call it, or a cold smooth or a reload patch. Now, most of our patches should live in the upper echelon here, which is basically 80% to 90% of these are non-reload smooth. However, sometimes we do hit a problem where it is within the kernel or it is within a major library like glibc. We have other problems. We have to deploy something unique, so we have to take the device down. But we will let you know, so this way you can decide whether you can deploy this during your normal hours, again, going back to your planning, or do you have to take a down window so you can affect it or replace it or maybe apply it a little bit later. So we'll tell you what it is so you can decide. Now, installing this move, very simple. There's a three-step process. First is the installation. It's the same install command we use for ISSU as well. You will put the RPM patch that we gave you into the system. That just puts it in your boot flash or wherever you're going to be deploying the patch from. The second part is activating the SMU, which is applying it into the network. This is when it takes effect. And a third step is committing it after you're happy and you've deployed it and you check that everything is working and everything is functional to your liking. Once you're done with that, you can commit it, then it becomes part of your mainstream. So if your device does happen to reload, or you decide to reboot it, or something happens, then the patch is automatically applied. You don't have to keep applying it every time onto your top of your software. Now, if something happens between step 2 and 3 before you actually commit it, then we will fall back and we'll reload the SMU. We'll actually roll back to a previous version of the state to make sure that your network was back into the same state. Because sometimes we deploy a SMU, and that may have an interaction with some configuration in your network or some other issue that we did not anticipate, and that causes a problem for us. So if we leave it in that state, your devices are not usable. So we actually decide to roll back and bring it back into a well-known state to keep the network sane. And then usually we get a TAC call. We're jumping back onto the switch, trying to figure out what the problem is, and a new patch is deployed or something else is happening. Make sense? Does that look good? Okay? All right. Let's take an example of a non-reload SMU. Reload SMU will be boring, right? I can just reload the box. I want to just talk about a non-reload SMU. So what we do in a reload SMU, remember I talked about checkpointing. All the devices are checkpointing their state to the persistent storage. In this case, when we're ready to do the install command and the activate, the system manager will stop that process and say, okay, that process is going to be reloaded. I will deploy the files in the right locations so that when the device boots or the process reboots, it comes back and applies all the new configurations or all the new libraries or all the new binary files that it needs to come up with the new version. And then, again, the data plane is not impacted because we're forwarding along the well-known paths because of the control plane, data plane separation. The state is recovered, and again, it's about 10 millisecond process. Very well. If everything goes well, you're happy, you will commit it, and then it becomes part of your mainstream. If you move to a new version of software, usually what happens with SMUs is we absorb them into the new version of the software. So anything that is part of the patches that was on 10.1, for example, 10.1.1 gets released, 10.1.1 contains all the previous SMUs. So you don't need to have them, we absolutely absorb them, it becomes part of the mainstream of the software. And we'll just build new SMUs on top of them if needed. Question?
Verify option for the SMUs?
The question is there a verify option for the SMUs? No, there isn't. There's only an activate. The activate is the verify. Once you deploy it, you can see if the problem goes away. If it's not, you don't have to. You can always roll it back, or you can just reload it. Yeah. Any other question on patching? Sorry, I didn't hear you. So the question is, can Nexus Dashboard do that? Yes. If you have Nexus Dashboard integrated into your ecosystem, then we can do everything I've told you here from Nexus Dashboard. Nexus Dashboard, you'll push the SMUs to it, and we'll talk about it. I think I have a slide that kind of shows a little bit. Let me go there, and if not answering the question, I'll come back to it. Any other question, guys? Yes. So the question, what's the policy when we roll these SMUs into the software upgrade? Usually we try to roll them into the next release unless there are unique patches that are like some specific reason. I'm not really sure what your network is, or is this like a unique case? Usually most of the patches are rolled into the next version of the software or the one after it, because maybe the next version may be already in the process, so maybe the one after that. But usually we try to roll them in. If it hasn't happened, I'd need to go look at that specific patch to understand why. Okay. If you can send me information about it, I can ask specifically why that hasn't happened. Maybe it just got lost in the shuffle. That's also a possibility that somebody forgot about it and they didn't apply it correctly, or it was maybe on a special release that we applied to your network and it didn't get rolled in. But usually we do apply them in the next version. Okay. Sir.
Is there like a compatibility or readiness check within that install command, or you have to like fully?
Yeah. So the question is, do we have compatibility checks? Yes, we do release a compatibility matrix for every release that we do for ISSU. So you can check your 2 version to the next version, where you're coming from, where you're going to, and it will tell you if this needs to be a double hop, needs to be a single hop, needs any smooths, all that stuff. We already have that. I have a link to it somewhere here in the slides, and I can send you the access, but it's actually online, you'll have it.
But nothing within the command automatically itself. You have to read through and make sure.
The question is it within the command? No. Only if you do an ISSU. Yes. If you're doing it on the patch, no. On the ISSU itself, it is. And actually, I'm going to talk about it right now. You just got ahead of me by 1 slide. So Okay, one more question.
I saw something like a super spine. Is it something coming up in the next slides?
So question about, is there a super spine? Yes, I'm going to talk about it in the network level. Give me 5 minutes. We'll get to the network level. You had a question? So the question is, does DNA support Nexus devices? I don't know to what extent we are actually playing with DNA. We do have it, but DNA is mostly for Catalyst. So we have our own controller, which is NDFC, not really on the DNA. We are starting to add cross-integration between devices that we can learn from the NDFC as well as NDNA, but I don't know to what extent they're doing, is it ISSU capable or not? I'm not really sure. Okay, so let's talk about ISSU. So when you get to ISSU, when you want to change your version of the software, the first thing you do is you basically copy the device, copy the image to the device, right? The second question is exactly what you asked, which is we run a command called check the impact of this upgrade before I actually apply it. And this is how it works. I actually do that. I'll give it the version of the new software. Internally, we have a matrix that is actually shipped as part of the code that will go and look at the compatibility between the first version and the second version, and it will determine whether this is going to be a graceful or an ungraceful upgrade. So we'll come back with an impact, and we'll tell you in this case, okay, this is going to be a disruptive upgrade, or you need to do a double hop, and it'll give you a reason. Then you can decide to fix that, whether it's a new command that was added, whether it's an old hardware that is removed, or some capability accordingly, so you can do that. That basically is the question you're asking. For ISSU, we do it, not for patches, though. Okay? So once you determine that, then you can decide if you need to take a longer window or go fix these problems before you come back. Okay? Now let's take an example of a hitless ISSU on the Nexus stores, right? In the hitless ISSU, since we are a single supervisor, right, we can do ISSU here. What happens is, I said, all the devices are checkpointing their state. We will basically start the install process. This is not working, okay. Once I install the process, I save my state. The device completely reloads. We do something called the K-exec, where we basically jump from the first version of the software to the new version of the software. Again, control plane is not impacted at all. We have a 0 packet loss in this case. That's the beauty of Nexus. We can do this with 0 packet loss. We are supporting only the data plane is fine, the control plane is rebooting. It comes back, and then everything is restored, and then I reconcile the hardware. You can see the dip in that window here. I don't know if you can see my screen, but you can see the dip at spot number 3. Does anybody know how long we are out for when we're doing this? Question, you reload in 10 milliseconds is one answer. I heard 30 minutes. Okay, now I wish we could do it in 10 milliseconds, and we don't even talk about it anymore. We can't do that. We would love to get there. I'll tell you where we'll do better, though. And it's not 30 minutes. That's a very long time. That's what Catalyst does. They do 30 minutes. Okay, now they've dropped down to a whole lot less number, but we do about 90 to 120 seconds of outage time. So that is pretty big. That's why we have to reconcile when I come back, and that's probably where NSF comes in the picture. I have to relearn a whole lot of protocols. I have to reconverge all my state. Now, can we do better than about 120 seconds? That's a long time, right? Because if I have STP or fast STP or fast LSCP in my network, that's not going to survive. It's going to basically be losing all its ports, losing all its connections and everything. So we can do something better. We do something called an enhanced ISSU, which is the new version of ISSU that we support. It is basically mimicking a concept of dual supervisors within a single tour. It's a cool concept. We got a nice patent on this one, too. It's pretty cool. So what we do is we create a container where we deploy the supervisor. We create a container where we deploy the line card state. And then during the ISSU process, what we do is we start the process. We create a second container. We use the concept of SSO. We synchronize between active and standby. When it's ready, we switch over. And now we're within 3 to 6 seconds. So not yet to 10 milliseconds. We're trying to get there, but 3 to 6. So that's a drastic improvement over 90 to 120 seconds, right?
So is 3 to 6 seconds or the 120 seconds, is it the data forwarding?
So the question is the impact of 3 to 6 or 120 is it data? No, the data plane is always intact. That's what I said. The control plane is the one that's impacted, not the data plane. The data plane is always forwarding. As long as there's no major convergence in the network causing an outage to the paths, you should be well along the well-known paths. So that's only control plane impact, where there is no data plane impact whatsoever. Still 0 packet loss. We're still talking about zero packet loss.
If I have the give us some time, but the
So the question is, if I have n device connected to this one, it's still okay because the data plane is still forwarding along the green lines that you see here. There's no impact. Only the impact is happening on the learn. So if I need to learn some new route or something happening, then I'm out for a little bit of time. Okay, and the reason we say 3 to 6, okay, so we can actually get lower. But today, the reason we say 3 to 6 seconds is because when I learn my control plane, I'm syncing it to the other side. I don't write it into the process memory directly. I'm only writing it to the PSS storage. So I have to take time for me to restore that state from the PSS storage into my memory. So this is more inside the scenes for you guys so you understand why we get 3-6 seconds. Now, if we can do it in the process memory directly, you're right on, we could probably get under 10 milliseconds, even 0. So, but we don't have that today, okay? Make sense? So this is a cool thing. Now, there is one glitch to this one. The only glitch to this one is if you have a kernel upgrade that you need to do, and it's not a small patch into the kernel. So if we have to change the kernel, that means we're moving from a version 5.10 to some new version of kernel, we need to still fall back and do it with the NDISSU way because there's no way for me I can actually restore everything and keep the kernel running without impacting the system. So unfortunately, that is something. We'll try to work on it and see if we can do better. Right now, that's the way it is. So if you have a kernel upgrade, and we'll kind of tell you, if you look at the matrix compatibility, we'll tell you, oh, this is not compatible. It's going to be that one. It'll fall back into NDISSU. Still zero packet loss. Still no data plane impact.
Is the kernel, is that the same thing as the EPLD, or is that something different?
No, the question is the kernel as the same as EPLD? No, it's different. I will talk about EPLD in a different way. Okay, so if you look at the devices here, so most of the devices we start deploying are actually deployed in LXC mode. So if you do this show output, you can tell if you're in LXC mode or not. The only way you can tell if you see there's something called the virtual supervisor module, and that's basically where we're talking about a container. So if you see this in your system, that means you're already deployed in LXC mode. Now, that doesn't mean you can't get to LXC mode in the previous versions of the software. Starting in 9 something, you can get into LXC devices. You just have to take one reload to get into it. So if you have a down window, you can do that. You can bring it into here. You don't have to actually have it. But you do require 16 gigs or more on your devices for LXC to work because of the container overhead that we have. You can't do it on 4 gig or 8 gig devices. Okay. I saw a question in the back.
Yeah, you just covered it. So in 10.4, is default in the containerized mode or
So-
the 9.3?
Yeah, so the question is the default LXC mode in 10.4? Yes, I think starting in 10.2 or something, we must have moved most of the devices to LXC mode. So if you've got into 10.4, by default, you're already in LXC mode. However, previous versions of the software, we had the option for you to leave it in the base mode, or you can come into LXC mode if you wanted to, because it required a reload. So if you're doing an upgrade anyway, we'll bring it into LXC mode automatically. But if you're not, then you don't have to. Does that answer your question? Yeah, okay, good. Okay. So let's go a little bit more forward. Like I said, you can do ISSU with NDFC or APIC as well. And the way that this works is we have a cluster of APICs or a cluster of NDFC. If you don't have NDFC, you don't have to worry about it. If you have ACI, APIC is there. So you basically deploy the software to the controller, and you can do all the stuff we've talked about from the controller itself. You can do that for just regular switch upgrades, or the APIC upgrade, or the NDFC upgrade itself. We send the devices, we'll send them, we'll do the ISSU there for you. Once you start the ISSU process, you can do it for multiple switches at a time. I have a whole session that dives into ISSU in detail on Wednesday afternoon if you guys want to come at 4 o'clock. It's 2639, I think, is the session number. That talks a little bit more about ISSU, because I can't cover the whole topic in here. I want to make sure I cover the whole network aspect as well. And then you can do the same thing for patching. And finally, you can do the same thing for EPLD. So the question about EPLD, is it different than the kernel? Yes, if you have an EPLD upgrade, we try to do it there. There is combinations of things that we have done to improve the reboot number of times. So you don't have to reboot EPLD and then reboot the SMU and then reboot the stuff. So and this is basically what this next slide talks about. Simplifying the process of upgrades. The question you asked in the back, sir, is basically covered here. We have most of our devices deployed in NDISSU for LXC by default. We've also added a whole lot more devices. Reducing the number of reloads, we've combined doing upgrades of an image with SMU, and also upgrading an image with EPLD at the same time and SMU all combined in one. So if you require a reload, we want to do it once. We don't want to do it 3 or 4 times for you, because you're going to be taking a whole lot of outage in your network. You have to have a huge window. So we've tried to do that. The versions of software are listed there. We want to provide, remember I talked about the kernel. So if we do a small patch in the kernel, we can actually cover that as well. With 10.2.2 going forward, you can do that and try to get to your LXC mode. If it's a whole kernel, that's still not covered. We still have to take an outage and go back to NDISSU. So far, so good on ISSU, guys? Are we good now? Everybody's happy? Did I lose you? You guys still awake? I know it's 8 in the morning, man. I don't know, how did they do this topic at 8 in the morning? The best day in the morning, but it's the best topic in the world. Okay, go ahead.
Over the years, I haven't got consistent guidance on when to do EPLD upgrades. Should we keep it in sync with the code you're running, or is it just when we do?
So the question is, I haven't got guidance on when to do EPLD upgrades. Okay, so starting in the new version of software, we actually put the EPLD as part of the image itself. You don't even have to worry about it. We will take care of it for you behind the scenes. But that requires you to be in 10.4.1, I think, forward. We do that together. Otherwise, you'd have to still kind of figure out to manage when you do your EPLD. We'll tell you, but you'd have to actually do it. But in the next version, starting in 10.4, I think, going forward, I don't remember the exact number, EPLD is part of the image itself. It comes integrated. You just do one command. If it needs an EPLD, it will do it for you. If it doesn't, it will not. So we're already taking care of that problem because we've seen the issue and we've handled it behind the scenes. Any other question?
Will line card support ISSU?
The question is, will line card support ISSU? Okay, so on N7K, yes, we did. On N9K, no, because we don't even support ISSU on modular chassis at all. And that's where the line cards are. So we don't even have ISSU on modular chassis in the first place. So that's the reason why we don't have it. If we do add it, then it'll probably be fairly similar to guidelines of what we did on the 7K. But right now, we don't have it. Okay, that's why we have GIR, and I'll talk about that in a minute. Let's talk about network level. Okay, so we've talked about within the hardware itself. We've talked about the software capabilities we have. Now let's talk about the network level. How do I do things on the network level that will improve my life, right? This is the old legacy way of doing it, V-shaped. I have a aggregation core, distribution layer, all kinds of stuff. You have to figure out where your STP primary is going to be, where your STP secondary is going to be, where HSRP is going to be. Usually they follow the primary of STP, where your secondary is going to be, all kinds of stuff. You have to deploy root guards, you have to deploy loop guards, you have to make sure your network is loop free. Okay, we've went away from that one. Remember I talked about that in the beginning. We are no longer doing this concept. We are actually going to the concept of this new paradigm that we call spine, leaf, and super spine architecture. Right? And the reason for that is we get multiple advantages. One is it's a scale-out network. So I can have multiple spines. Like you see here, I can actually have 4 of them. I have multiple leaves. The leaves are just nothing more than my breakout ports or my number of ports. So that's where I get my scale-out. Right? The other advantage I get out of this one, the N+1 redundancy, which is more relevant to this session. Because now I have 4 spines. Before I had 2. So if you have an outage, FHRP would have to figure out how to move all the stuff that is happening on the spine or the core layer into the second one, replace all the IP addresses, replay them back. It's a big, big table, learn everything from the MAC and ARP and everything like that. This network provides a couple of things. One is I can do more spines on the top, so I can get less failure of redundancy. So it's not 50%, I can do 25%. If I do 8, I get 12.5%, so forth. The other advantage is everything is learned on the leaf. So my MAC tables, my ARP tables are much smaller. I don't have stuff in the back. The back is nothing more than just my interconnection to the world. This is where I pass my traffic. Everything is done on the leaf, so the tables are much, much smaller. So if a failure does occur, I can actually do convergence much, much faster. So this is one advantage of using this network as well, right? Besides the scale up. Now, the other thing that we want to talk about is how do I evolve my journey? I talked about the modular concept versus the spine being a fixed form factor, right? So, and if you look at the left side of the picture, the first part, I deploy leaves as stores, which is top of rack devices, and my spines are deployed as modular devices. Cool, this works. We've done this before. You guys have done this before. I'm sure it's all over the world. It's in the network. It's been proven it works. There is nothing wrong with it. You do it. But if we flip the network on its end and we look at it from a different angle, right? I can add a third layer. Now, because I have controllers in the network, I don't have to worry about how many layers of network do I have. Do I have to worry about having 3, 5, 7? I don't really care because the management and the control comes from the controllers. So that's an advantage of AI coming into the picture. That's an advantage of controllers coming into the picture. So we can actually add more devices. I can add another layer, call it the super spine, and in that case, I can do modular as well. Now, do I get latency problems? Yes, there is latency problems. So let's look at if I go to a third model where I deploy everything as fixed form factors. So if I use TORs across all three of my layers, like the leaf, the fabric, and the super spine. So if I look at the hops that happen in the ASICs, right, from the itself on the device, there's usually one ASIC on every TOR. So the entry of the device comes in, I hit the ASIC once, then I go to the second layer, I have to exit that ASIC just once, go back to the top, come back down, so I can do it in a 5-stage process, much, much faster than having to do it in an 11-stage process here. So if I do it here on the left side, it's 11 stages, because each one of those modular will require 3 hops. I have to come into a line card, I have to go to the control plane, I have to come back to a line card. So if you add that up, it's 11. So the bandwidth and the latency, I can do much faster with moving to fixed form factors. So this is the new design. This is the new paradigm that we're actually shifting towards. That's why you were asking about the modular chassis. So if you have them modular there, if you have connections with PCs, you don't really need redundant supervisors. If you move this way, you don't have redundant supervisors to start with anyway. You will have to live with it anyway. So you don't really need it. It depends how you deploy and what you're planning for your network. Does this make any sense? Does the shift look cool? It gives you a couple of advantages as well. One is speed, one is latency, and the other one is cost, big time cost. Fixed form factors are much, much cheaper than modular chassis. Now, as Cisco, I want you to guys buy as modular as you can. We want to make as much more money as we can. But that's not the goal of this session. What we are trying to teach you here is how do you make your network more resilient, because the less stack calls we get, the more money we also make. Trust me, it's an advantage for us to have your network more solid, because you'll keep coming back to us as well and say, okay, I'm good, I want to keep deploying this network. We don't want your network to fail. This is the whole point of the high availability story. So I'm not trying to sell you anything. I'm just trying to teach you all the stuff that you can. And again, every network is different. It's not going to be when you do this and you're done. Everybody has their own unique way of doing it. Question? So the question is it a role? Not really. I mean, you can call it spine if you want. You can call it leaf, spine, super spine. We kind of, just to distinguish, we call it leaf, fabric, and spine. So F stands for fabric layer, because we deploy things in fabric modes. So we no longer deploy things as single units. We deploy things in fabrics. And I'll show you how we do that in the next slide. So give me 1 second. Question?
So, on your traditional, your core distribution access, it's usually layer 2, right, between the distribution and the access. And here, it's all layer 3 between all the devices, right?
Correct. The question is it layer 2 or layer 3? Well, it depends. If you have VPC in your network, you might still have layer 2 there, because VPC runs over layer 2. We don't have layer 3 VPC today for Nexus.
So you can deploy VPCs over...
You deploy VPCs, absolutely. So the question is, can you deploy VPCs here? Absolutely, we do VPCs here. VPCs is a very critical part. I'm going to be talking about it next. So we do VPCs all over the place. It's a huge thing, especially in ACI network. Everything is VPC pairs, because we don't have ISSU. We have no choice but to deploy VPC pairs. Okay. So like I said, this is the new paradigm. Sorry, you had a question. Go ahead.
So the previous bit with the super spines, and if you have an EVPN fabric, the leaves will remain the VTEPs, right? And then the spines will be just forwarding, nothing else. No VTEPs on the super spines.
So the question is about the EVPN. I don't want to answer that question because I am not an EVPN expert. Okay. So I don't want to confuse you. If that's what it is, then maybe that's true. There's multiple EVPN sessions being offered today. I think Lucas and Mateus and all these guys are offering a session. You could maybe go to that one and find out. I'm not really sure about the VTEPs exactly. I don't want to confuse and answer in the wrong way. Question?
All series of the Nexus line up, they do each, can they be a fabric, can they be a spine?
So the question is, can all the Nexus devices be replaced at every layer in this topology? I would say no, because some devices have different bandwidth, right? Some of them are like 10 gigs only, so you probably don't want to deploy those in the second layer or the third layer. Some of them are 40, some of them are 100. Now we have 400, now we have 800. So you probably want to use like 9400 series and above in the top layers, and then 9300 and below in the like second or third layer. I'll have a slide at the end that kind of shows where you can do which of them, but it depends on how much bandwidth you need. I mean, if you need 800 gigs, you're going to have to go with the 9500 series. You cannot really go with a 9300, it doesn't support it yet. So all of them have different bandwidth and different modulars and different stuff that you can plug into them. So you have to look at that and play with it accordingly. Does that answer your question? So I don't want to say it's like, it depends because that's the normal answer, but that's really how it works.
The super spines, what do you think? Like, it is unredundant devices, or they can swoop?
So the super spines, is it redundant or non-redundant? If you're deploying the left side of the model, then they're modular, they could have redundant supervisors. If you're deploying the right side of the model are Tor devices. They're fixed form factors. They don't have dual supervisors, single supervisor in each one of them. So the circle means it's a Tor device, square or a triangle, rectangle means it's a modular device. Okay, so fixed form factor.
That is the case in case of the top layer failure. Let's take it as a
So-
one color plate fails. It's gonna
So the question is, can you hold on 2 slides? I already got discovered, so I'll talk about it. So if we start looking at it from this concept, right, like I said, we want to do this in a scale-out fashion. I want to build my fabrics one at a time, deploy it, then replicate it, and then continue to do that. So if I do that, I can actually do modular, hierarchical, all kinds of stuff. So let's see how we do that. So if I go back and step into this device and design it with the fixed form factors, the first thing I want to do is make sure I don't connect all my ports. If I connect all my ports, I'm done. There's nothing I can do to get to the third tier. So you don't want to connect all your ports. You want to leave as many ports available to go to tier 3, as many as ports as you have to go to tier 1, right? That's the first thing you want to do. The second thing you do is you want to do more scale out. You can deploy more fabric. So each one of these boxes we call a fabric, and hence the name of the F switch that came in. Why is it fabric? Because they're deployed on a fabric layer. Then I connect them to my third tier, which is the top layer. Now we actually can segregate my traffic with MPLS SR as well, where I can actually do an ECMP solution. I can connect them there. Now, if I stay here at this picture and one of those fails, your question is relevant. I am going to be in trouble because I have nothing there redundant for me. But I don't stay here. I actually move on one more level, and I can deploy multiple levels of N+1 redundancy at the top layer as well. So if I have that, now I'm at basically 4 devices here, right? So if I have 4 of them, I have 4 paths where I can get out. So I'm at 25% possibility of failing. If I do 8, then I get better. So this is basically where we do this, where I can scale out. I can do this. Everything I've talked about, I'm just kind of showing in this picture right now. Does that make sense, guys? Lower cost. The advantage of this one is amazing because you can do this with lower cost. Like I said, I would love to sell you as many devices as possible, but that's not the goal. The goal is to make sure you understand and how to deploy this. This is the new form. This is what Google does, Facebook, Microsoft, Cisco, all the new titans of networking. This is the new deployment factor that we're actually going towards. Now, does that mean I want you to go into your network as soon as you leave here and start taking all your modular devices and replacing them? Awesome, you can do that, then please do, but it's going to take you some time to move to this new evolution, right? If you're already deploying new networks, this is the new model that we want you to do. Great?
Very big, huge deployments. And if you're looking at a smaller deployment, does it make sense to do this?
So the question is this required to be for new deployments or smaller deployments?
Huge.
For huge deployments or small deployments? Not really. It's your choice, right? You can still do it on the smaller factor because you can only deploy one small fabric on the left side, like fabric 1 only. You don't have to deploy multiple fabrics if you don't need it. You can do 2-layer. You don't need a 3-layer. It's up to you. Depending on how big your network is, you can do it. But if you have an existing model, then just go with it. There's nothing wrong with that existing model.
My question is, this 3-tier model, does it only fit for the big players like Amazon, Google?
So does the big tier model fit for Amazon, Google? I mean, I don't know how big your network is going to be, so I can't really say. But yes, most of the big players like the Titans use this. Now, do you really need it in your network or not? I really can't tell you because I don't know exactly your configuration. If we talk about it offline, maybe we can discuss and figure it out. Okay, any other question before I move to VPC? Okay, good. One more question. Go ahead. It's okay. That's why we're here.
do we
The question is, do we need any more interconnection between the superspines?
Yeah, but within that,
So you're talking about this picture right here.
as the group, right? So we need any disconnect.
Do I need a connection between all the greens or all the blues or all the reds separately between them? Not really. You don't really need it because you have multiple paths coming into it. Usually you have another end of the network going to the other side, right? So you don't really need something else like this because as long as you have a path out, you're fine. You can get to that device and then continue on your merry way, or it maybe comes right back and it's going out the same side. I don't know where the exit port is going to be for the ingress, where the egress is going to be in your network. So you don't really need connections between them.
And depends on what's the uplink for that.
Correct. So the question is, what is the uplinks for that? Like I said, we support up to 800 gigs now, so most of these guys are really, really huge. So if you start connecting between them, you're probably going to need a whole lot of bandwidth. Let me talk about VPC. You'll see a little bit more about that when I get to it. Okay. Let's get to the next one, which is there. So one recommendation for route servers. You can deploy route servers in your network in two ways. You can either do them in line, which is cool because you can just take two of your fabrics or your super spines and make them route servers. That's good because they're in line, the traffic is there, any failure or detection you can do there, no problem. However, if you don't deploy third-party route servers, then you can't do it that way. You'd have to basically connect them that way in a separate manner. So you can deploy them anywhere in the network. The problem with that one is the latency for detection, and you'd have to depend on BGP reflection to tell you that, okay, you've lost the route server or something like that. So if you do it the first way, it's in line, but if you have to deploy third-party route servers, then you'd have to go the second way and depend on BGP for you to detect the outages. Question? The question is, what's the role of the route servers? They are basically learning your routes and advertising into the network. So these are like your border control gateways in the site. So you can learn and then deploy them in the network. So it depends. If you need this, you have two ways to do it, either separate route servers for third party or inline service for the network. Okay? Let's talk about VPC. So VPC is definitely needed for our devices, especially when we go to the new paradigm. The reason we do that is because I mentioned all our Tor devices or top-of-rack devices are single supervisors. So we don't have ways to protect them if they fail, especially if you have other problems. The good thing is you can do ISSU on it, but if there's other failures, you may need another path into the network. So that's why we have VPC. This is kind of a fun way of doing VPC. We have dual control plane, so that the control planes are active. They're completely different, but the data plane is merged, right? So you can see it from the outside device as a thing. But we do have dual control planes, so we have to actually control them separately. They're not controlled similarly. So if you're used to the Catalyst to have a VSS, if you use the VSS merges both control plane and data plane. We don't. We also do L2. They do L2 and L3. So we only use LSCP, they use PAGP. So there's the differences between them. So if you're familiar with the Catalyst side, you know what that is, but that's not what we have here on this side. So we have L2. And this is kind of answering your question, sir, at the beginning. We do have support L2 because of VPC. And then basically the traffic is symmetric. So the cool thing about the VPC is the traffic can come into either one of the VPC pairs. The BPDUs can be handled, and they can go up. They don't have to cross the path to go from one side to the other. So we don't need to use that bandwidth in between those devices. Now, for VPC overview, this is just more terminology. I'm not sure if you want me to go through this, guys, a little bit. This is kind of saying, okay, this is the domain. This is the two devices. One of them is considered the primary. One of them is considered the secondary. They have a peer link between them. This is where we can send control traffic. We use something called the CFS protocol, which is a protocol to send messages over TCP across active and standby. Then we have the VPC keep alive link, which is basically another layer of detection to prevent the devices from going down. I'll talk about the failure cases in a second. You'll see where this comes in the picture. And finally, you'll have the VPC channel, or like similar to ECMP or something like that. This is called the VPC channel, where we connect them into port channel configurations. If you have orphan ports, then they're connected into one side or the other. This is where sometimes you can have an interesting layer to determine what you're going to do with your orphan ports or orphan devices, because not all devices are capable of connecting to two devices. Now, if we look at the roles of the VPC roles are determined usually by setting the priority of the devices. But since we send them into the field with the default configuration, all of them have the same priority of 1. So we need something else to tie break if you don't change your configuration. If you change your configuration, then the higher priority will always win and becomes the primary. The secondary becomes the secondary, very normal. If you don't, then we use the MAC addresses. So if they both have the same priority of 1, the MAC address of the lowest MAC address wins the election and he becomes the primary. Now we have something called the operational role. So the cool thing about VPC is it's not preemptive. If you have 2 devices, let's say you've configured a primary on the left side and a primary or a secondary on the right side, and you have a failure in the network, then the secondary will become the primary in the network as an operational mode. Even though he's configured as the secondary device, he is considered the primary for the operational mode, and that's where the PPDUs are being detected, and he's the one who's processing the PPDUs. So that's where that comes into the picture. So to keep that in mind, it's non-preemptive. Like I said, the role is set like this. You can set the priority. You have a value between 1 and 65,000. By default, the value is 1. If you don't change it, you don't need to, but it's up to you how you decide to keep your network consistent. If you do show VPC on the bottom, you can see that in this case, I have a VPC role. It says, I am secondary configured, but I'm the operational primary because something has happened in my network and I'm processing the BPDUs. So you can tell whether you're the active or the standby and who's doing the messages. You can also force a switchover if you want to revert that, but you don't have to. We don't automatically revert back. In ACI, this is where VTEPs come in the picture, right? We do use VTEPs for ACI. We don't necessarily have a concept of a layer 2 in between the ACI networks because they're done like that. They're connected through the L3. So we do it that way. We don't really need a main channel that's going through the network. But the keep alive is also done as a separate thing. They use VTEPs in this case. So it's a little bit different. We don't use the concept of CFS. We use some open source called IFS, which is the new protocol that is open source for sending messages back and forth. Why was it added? Because this came from an NSEMI, which is an acquisition by Cisco. They did it a little bit differently than we did it. So it was built on the same story, but it was acquired afterwards. Okay, so it was done in a different fashion. Now, I mentioned this already. I talked about the VSS versus VPC. We do merge the control plane and the data plane for VSS. So if you're familiar with Catalyst and use Catalyst, this looks like this. If you are using Nexus, then it looks a little bit different. We have dual control plane and dual data plane and one control plane. Dual control plane and one data plane. The data plane is merged, but the control plane is not. We have L2, LSCP. They use L3 and LGP as well, right? Now let's look at the failure scenarios. I'm going to walk through these pretty quick. They're very, very simple scenarios. I have 2 VPCs connected in my network. You can see that the peer link channel falls. If the peer link channel falls, then I still have the keep alive. I can detect that everything is working. In this case, the secondary will basically take a drastic role and shut down its VPC ports so that the traffic doesn't continue to flow through it because there is no connection for me to configure or send control plane traffic across the board. So the BPDUs continue to flow towards the active with no problem. I don't have to do anything. There is really no change here, it's just detection. There's an alarm that you know, so you can go fix the peer link and bring the system back, and then you have complete VPC back up and running. Now let's reverse the situation. Let's say we fail the peer link or the keep alive link. Again, because the peer link is there, the same situation happens. There is no problem. The traffic continues to flow. There is nothing really that needs to change. My symmetric traffic can continue to flow. I'm just lost the keep alive, but I'm still able to talk to the other device. Both of the roles remain the same. There is no change. Okay, so far? Question? So the question is, in this case, do I shut down the VPC peer? No, I don't, because I do still have control plane running over my peer link, so I can still keep him. It's just that I don't see him over the keep alive link. But as long as I can talk to him and send him data plane, the control plane can be synchronized, so there's no problem at all. We keep it running like this. We don't want to cause any drastic situations if we don't really need to. Now, the third situation, let's say the whole peer goes down itself. The actual primary goes down. In this case, very simple. The secondary switches, and it becomes the primary. He's the operational primary, but he's configured as a secondary role. And then the traffic will flow through him because he becomes the primary, so everything is fine. The standby is gone. When it comes back, he becomes the secondary operational role as a primary configured. Now, there's one interesting case. Actually, no, one more after this one. The secondary goes down. No changes here. Not a big deal. My traffic continues to flow. Everything is good. Okay. Do I need to go through this? Pretty simple case. Okay. The case that's fun is this one. If I lose both connections to the other side, then the primary is primary, and the secondary will also take on the operational primary, because he doesn't know if that guy is gone or he's there. I would need a third-party intervention in this case, like a controller or some other device to tell me that he's still there. There is nothing we can do from the switch itself. I need a third-party intervention. We've talked about this many times, and every time somebody asks, why can't I just do something drastic? Unfortunately, I have no clue what the status of the peer looks like, so we both become primary, and in this case, it's an undeterministic behavior of how the traffic will flow. You might see duplicate packets into the network. Okay, so this is an undeterministic behavior. It's not normal that it will happen, that's why we have multiple layers of protection, but if it does happen, you will end up in this situation. Okay? So the question is, have we considered doing wireless interconnection in these two? Good question. I will take that into consideration and ask them. I don't think we have. I don't know if there's anything in the plans. I'll find out. Yeah. Okay. I'll ask. I don't know. I don't think we have, but we'll look. Okay, we're about 7 minutes, guys, so we're almost there. Okay. One thing about VPC member recommendation. Oh, you had a question. Sorry. Which scenario is it? This one? Sorry, I'm going back through many. That's okay. It's okay. This one? Are you talking about this one or the one before that? Okay, this is a peer link down, not a. Yeah, this is a peer link down.
Oh, so peer link failure, link loss between the two. So how is the keep alive up to connection?
So no, the keep alive is running over a different channel. It's not running over the same peer link. So we have two channels. We have a peer link channel and we have a keep alive channel. So as long as the keep alive channel is up and running, there is no problem. Yeah, they're independent channels. We keep them for that reason, because otherwise, both become the same problem. I end up in the last scenario, which I don't want to do. So we keep them separate.
Quick question. Does the preempt work here?
So the question is there a preemption that works here? No, we don't. We're not preemptive. Once we switch over and become the operational primary, I stay that way unless you force it to go back. So we don't preempt and we don't fall back. No, there's no preemption in VPC. The question is what? The question is VPC coming to the Catalyst line? I don't know why they would do that. They have VSS, so I'm not really sure why would they do VPC versus VSS. Like I said, the reason I put that slide to show you where VSS, VPC, they have their own method of doing that one. So Catalyst has VSS. We have the concept of VPC. VSS may be superior to VPC, or maybe VPC is superior to VSS. I don't know. It depends on your network, because we have L2 versus L3. So I'm not sure they will do it. I can ping the guys on the Catalyst and ask them if they would do it. But I would doubt they would actually change VSS to VPC. It would be a lot of work, and interoperability becomes a nightmare. Yeah. Any other question? Okay. Okay, one more thing left. What is it? Where am I? Let's see. Okay, VPC, plain recommendations. Like I said, because of the new devices, we recommend that you have a huge path between the control plane fabrics, 10 gig or more. Now, there is a calculator that is in the notifications or in the manual and the instructions that tells you how to calculate the bandwidth you need. Now, with 800 and 400 coming into the picture, 10 gig is probably not sufficient. You probably need a 100 gig link between them if you're using as VPC pairs. So there's a calculator that kind of tells you. You can go online at cisco.com and find it. If you don't, let me know. I can send it to you. It's actually in the documentation as well. It will tell you how to calculate what bandwidth you need between those devices. And then keeping the keep alive, like I said, separate from the peer link is important, because we don't want to get into this unknown situation. And finally, the last part is, like I said, we use LSAP. Make sure you dual attach all the devices. If you have an orphan port that is connected, unfortunately, there's nothing we can do about that until these devices become much more capable. Hopefully, you don't have a VPC failure and you switch to the other side. But if it does, then you might have an outage for that orphan port. One more thing left to do is GAR, right? Remember I talked about that we don't support ISSU on the modular chassis. So if you have modular chassis, what do you do? There's a concept that we have that's called the GAR, which is graceful insertion and removal. This allows us to take a change window where I can actually force the traffic to go away from my immediate device on the left, switch it to the right, and then you can replace that device completely, or you can upgrade it. You can switch the boot variable and reload it. You can do whatever you want to it because the traffic is flown to the other side. As long as you're not oversubscribed and you have this, it works. You can have this happen in VPC pair. It doesn't have to be VPC pair. Both of them can work fine. Once you're done, you bring it back. It's the same thing. You bring it with a single command, and it'll come back to the other device and it will start working. And then we have actually come up with an intelligent mode. So original GIR insertion was very, very rudimentary. You basically force the traffic to switch by shutting down all its ports. So if you shut down all its ports, the traffic will automatically switch to the other side. However, the problem with that one is if you come back into the network, it takes a long time for convergence to occur because now you have to relearn everything. You have to run all the protocols. You have to reprogram all the ASICs. So we came up with something more intelligent in 7.3. We're starting 7.3 forward with GIR mode. We call it an isolate mode. This is the default mode that we do if you do enter into GIR mode. It allows you to still force the traffic to the other side by maybe setting the bit in the IS path or setting the OSPF to the longest path or setting something there where the traffic will not flow into you. You still learn it, but the traffic will go through the other side so you can still do the stuff you do. Now, if you are replacing the hardware as a whole and swapping it, it doesn't really matter because you're going to come back and you have to learn everything. But if you're doing it with just a software upgrade, then the paths are still being learned, everything is being programmed. So when you switch back and you bring it back in the network, the convergence is much, much, much lower. Okay, makes a lot of sense. So this is one way to do it with an isolate mode. Graceful insertion removal recommendation. We don't recommend that you do a whole lot of stuff. You can change the window. Usually it's 20 minutes by default. We are asking you to change it to 60 minutes if you're doing GIR because now the image sizes are a little bigger and it takes a little bit longer. So you can configure that according to your network. That makes a lot of sense. One more thing about the last picture here. This is how we do upgrades in the network. So if you do it on the bottom layer, like I said, we usually use fixed devices. On the top layer, you can use fixed, and even at the topmost layer, you can do fixed or you can do modular. So then on the right side, it gives you the capabilities that tells you what you support. If you are using fixed, you have the capability of ISSU. You do have still SMU capability for all of them. You still have GIR capability for all of these capabilities. So you can choose to do whatever it is according to where you are in the network and whether you're deploying a modular versus a fixed factor. Like I said, the NUMA recommendation is to go to fixed form factors. But again, your network is there and it's been there for a while, so you may be still using modular. So remember that ISSU is not supported on the modular devices. That's it. I think we're done. Question? So the question, does the GIR support cover control plane on the other device? It does not. It does not cover the control plane. So guys, before you leave, please make sure you put your evaluations. 5s are good, 1s are bad. And we want to hear your recommendations on anything we didn't cover or anything you can do. Thank you for your time. Enjoy the rest of the day.